So welcome to lecture 17. This is going to be on PMOS and bipolar transistors. So the first lecture of a few on bipolar transistors. As usual, why does that keep coming up? As usual, we have a few announcements first. So your homework is online and due Friday via Gradescope. Lab number 3, I guess you're doing that now. The pre-lab for that's going to be due next week. Yes, and the lab number 3 experimental part will be due the week of 10/19. Okay, here's this thing again. All right. And so lecture topics today, again, we'll finish up MOSFETs and MOSFETs and talk about the body effect, which is what I started with last time, and then start talking about PMOS, which is sort of the opposite of NMOS, but works pretty much the same way. We'll then take a look at the other transistor that we'll be interested in, which is the bipolar junction transistor, regions of operation, cutoff, forward active. But before getting into any of this, is there any questions about things that are going on in the class or logistics? How's everyone doing as far as the labs are concerned and the homeworks? Is everyone doing all right? Is the workload okay? Okay, no one is saying anything, but I'll probably try to get more data on this sort of thing in other methods. Okay, I got one thumbs up here. Okay, so that's good news there. I just want to ask those questions because this is a special semester. It's you're all doing it remotely, and so that introduces additional hardship, I suppose, for a lot of things here. I should say also that your lab number 2 experimental part is due, I guess, today and tomorrow in your labs there. I guess I should have that on this. So let me write that. Okay, so last time we were deriving the saturation region of the MOSFET equation. We finished doing that. And now I want to continue talking about some second order effects. But before doing that, let me first just go back to where we were. That was all the way back in Friday, so I don't know if everyone can remember everything. So we're discussing the saturation region. And that's the region where not only is VGS minus VT greater than 0, which means our gate voltage VGS is greater than that threshold voltage that we talked about, VTN. So that means that the channel has formed. I have a channel of mobile carriers, in this case electrons, for this NMOS device. It's NMOS because I have N plus source and drain. But in addition, the voltage across my drain to source is now larger than VGS minus VTN. And we talked about what happens when you have this particular set of voltages. What happens is we pinch off the channel of mobile carriers here. And what that does is that means as I continue to raise my VD versus VS, that doesn't increase my current across this. And so we plotted out the curve for that, which looks something like this, that this is ID, the current going through the MOS transistor, versus VDS, which is the voltage across that the drain and source of that transistor. But you'll notice that when VDS is small, so when it's less than VGS minus VTN, the curve looks linear. But when I get to that point where VDS equals VGS minus VTN, things change. I get that pinch off, and this flattens out. Ideally, it flattens out. But we also talked about how last time what's really happening is as I continue to raise this VD past VGS minus VTN, then this voltage becomes higher than VGS minus VTN. VGS minus VTN is right here. And if it's right there, that's where the channel pinches off. So that was where I have a lot of mobile charge here. I have no mobile charge here, but the charge could still flow across here. Right? And so now effectively, the length between my high voltage and low voltage here becomes smaller, which means that my channel length gets smaller. What I'm integrating across gets smaller, which means that my current goes up. And that's something we saw then in deriving this equation. So we derived that equation last time as well for the case where VDS is greater than VGS minus VTN, and it ended up being this equation right here. So this now is the standard equation for a saturated NMOS transistor. And so I know what you're looking at right now. You're just looking at an equation here. You know the physics behind it, or you know a lot of the physics behind it. And when you go to 130, what you'll find is you'll go even deeper into the physics. You'll start talking about energy band diagrams and different physical concepts that help you understand at least the statistics that led to a lot of this stuff. But you'll see that we have derived most of the important stuff right here. Everything that you've seen so far is what you need to know to understand the physics of this device. Now, if that physics was too much for you, hopefully it wasn't. We're going to sort of force you to think about physics in this week's homework and some of next week's homework. You need to get some of that physics, but I guess I could even say that if you get none of it, you're still going to be able to do this course, because later on, when we start handling circuits of these NMOS transistors, we're not going to be thinking about the physics. We're going to be thinking mainly about looking at the topology of the circuit, and again, being able to analyze it in less than a minute. And you can't really analyze it in less than a minute while thinking about the physics. And so you'll be able to do that without thinking about the physics. But it's important to know the physics, especially if you're doing things like future design, designing a new type of circuit, which some of you may be doing here. When you're doing that, usually those who know the physics are able to get the best designs. You know, if it's one company versus another company, of course you want the best design versus, say, your competitor company or so. And so this is the equation that dictates that current. So it's really what voltages you're applying, the VGS voltage, the VDS voltage, and how when applying those voltages, you get a certain amount of current out of this. And you'll see that later on when we talk about circuits, that will be very important. So this is the last thing we talked about. And then I kind of scooched on to the next topic, but didn't go into it. And the next topic is that threshold voltage we've been talking about. So this voltage VTN. Okay, I'm not going to give you the pure physics behind what sets that VTN, but I will give you the equation in just a second here. The pure physics takes longer. It takes a week or so or more to derive. That's something you derive in 130. But you're soon going to see the equation for that VTN. But first, let's talk about a few characteristics of it. So what you know about it is that it is the voltage that the gate voltage has to get over in order to form that channel. And so if I take, say, this cross-section here that we've been looking at for a while, and I go ahead and put some voltages around this. So I'm going to put ground here. I'm going to put a VG on here. And let's say that VG is going to be, well, yeah, let me say the VG is greater than VTN. So say I put a VG here that's greater than VTN. And VD, I can put any VD. I could put ground or whatever VD I want to put in that. But you know that what happens when I apply this is I form that depletion region. So there's that depletion region. Because this is a P-type silicon substrate, that means there's holes all over this. But when I apply a positive voltage on this, so I put some positive charge here, what that has to do is induce an equal and opposite negative charge in the substrate. So all these things I'm talking about, we've talked about already, but I'm sort of doing this to help jog your memory and review a little bit. So with the positive charge on the gate, I put negative charge in the channel here, and the easiest way to get negative charge at first, remember, is to push holes away from the surface. And so this is pushing holes away. All of these things I had drawn before in a previous lecture. But then at some point, as I keep raising this VG, it becomes easier to create negative charge, not by pushing holes away from an interface that's now much further from the gate oxide here, but it becomes easier to form that charge by, and I wonder what I'm doing this in another color here. Let me be careful about that. Let me do this in blue right here. By forming a channel right up here. So this is now a channel of electrons. And all of this is not new to you. You've seen this already in previous lectures. And so what I'm interested in here is, and I guess I can move this a little higher too. Let me go ahead and do that because I want space below here. I'm interested in what voltage do I need to make all of this happen here. So one thing that I know that could happen is, suppose I went in and I applied a larger voltage than I have right now for VB. So right now, the picture that I've drawn, say that that's the picture for the case where VB is 0 volts. Okay, so remember, VB is a voltage applied to p-type silicon. That's connecting to this N+ silicon. So this is really creating a PN junction here, right? And the PN junction is in this direction, right? So I have a PN junction there, which means I have a diode in that direction. So I can't let P, the VB voltage, the voltage on the P silicon, I can't let that VB voltage get too much higher than VS. Otherwise, I'll turn on that diode. I need that diode to be back biased. Okay, and so say I suppose I start with VB as 0 volts, but then I move to a VB that is negative. Some negative voltage. Okay, if I do that, basically I'm making VSB bigger. Right? So in other words, I could say that what I've done is I've taken VSB and increased it. Okay? So what happens when I increase that VSB? So I've made it bigger. That means I make VB more negative. That means I could support more negative charge down here. And since this is a PN junction, if I'm reverse biasing the PN junction and I put a larger reverse bias voltage across it, what happens? What happens is my depletion region gets bigger. And so you can remember that from our previous lecture on this. And so with this larger VB, what's going to happen is I can draw a new depletion region that now may be this big. Okay, and basically I'm putting more negative charge here, and it's all static negative charge due to atoms that cannot move freely in the lattice, but we've taken holes away from them, or alternatively you could say that they've absorbed electrons. That's part of the more physical thing that's going on, that you've absorbed electrons there. And in this case, what I've basically done was put more negative charge in the p-type silicon here. So when I've done that, I've basically said that at least on the silicon side, say I wanted to write an equation here equating my charge. On the silicon side, which I could say has a charge equal to minus Q silicon, okay, and so that this Q silicon, that's a negative charge. What that is equal to is minus all of that inversion charge that I have up at the surface. And so this channel of electrons that I talked about here, that's Q inversion. Okay, plus all of that depletion charge that I have, that's the fixed static charge. So this is due to electrons here. Q inversion is due to electrons. And this Q depletion here is due to fixed charge on acceptor atoms Remember, acceptor is a name we call the type of dopant atom that comes in and accepts electron. That lost their hole, or alternatively, in other words, that gained an electron. Okay, so I've got a total negative charge that consists of this mobile charge due to electrons plus this fixed charge here. And what I just said is that if I increase VSB, what I just did was I increased this fixed charge here. Okay, and remember, all of this charge, that has to be equal to the charge on my gate. And so let me go to this color here and just say that I can equate this whole thing to plus QG, which is the charge on my gate. Okay, so think of what's happening. If I increase this, well, if I increase VSB, which means I decrease VB, I'm making it more negative. What's happening? I am increasing this Q depletion. Let me go on the other side to give myself some space here. So if I increase VSB, and let me do that in green, then what happens? The depletion charge in the silicon, at least the absolute value of that, the magnitude of that, that's going to increase. Which means that the total charge in the silicon, the magnitude of the total charge in the silicon increases. In order to support this, and here's where I'm going to color code again. Let me go back to this color. So to support that increase in the charge in the silicon, QG, the positive charge on the gate, must increase. Okay? What does that mean? That means that my voltage VGS had to increase, which means that effectively the voltage needed to create that inversion channel VTN, my threshold voltage, had to increase. Okay? And so that, what's that telling me? That's telling me that if I reduce VB here, which increases VSB, okay, then I have to conversely increase VG. I have to put more charge on the gate, which I'm showing right here. In order to get the same amount of inversion charge QI and V, absolute value, the magnitude of QI and V, right? So if I increase the C depletion, but in order to support this, okay, so this QSI goes up. I should be clear about that, assuming we have the same we maintain the value of inversion charge, which is what's allowing the current to flow. Okay, so how can we directly control VB if there are only terminals for VS, VG, and VD? No, there's a terminal for VB too. There is not just a terminal for VS, VG, and VD. For all MOS transistors, you generally have a terminal for VB as well. Okay, so you will always have a terminal for VB. We don't always show it because oftentimes we assume that it is connected to the lowest voltage in the whole circuit, which could be ground, which could be some negative voltage. Okay, so hopefully that answers the question in the chat. Okay, so what I'm basically saying that is if I increase VB, my threshold voltage is going to increase. And I went through the physics why that happens. And so now let me just show you the equations that dictate that. Okay, so the governing threshold voltage equation looks like this. VTN is going to be equal to some VT naught, which, you know, that depends on a lot of physics. That's the part that you're going to take a few weeks in 130, even in 230B to do it correctly, to determine what that VT naught is. But VT naught is the value of VTN for VSB equal to 0 volts. I know that doesn't say much. Doesn't tell you where it's from, but you can get that in 130 if you take that. The more important thing for what I just talked about is this part of the equation where you can see the dependence on VSB. And that if I increase VSB, that's going to actually increase VTN, at least for this NMOS transistor. And so with this as a body effect parameter, again, that depends on doping concentrations and other physical parameters. And then this surface potential parameter, you've seen this before, actually, the phi f. But I just threw it at you. I did not derive it. So all of these things you derive in 130. And so I encourage you to take 130 if you're curious where these come from. If you're not, you can use this equation because we'll give you these values whenever you need to use this equation here. Just some remarks to give you values for a typical NMOS transistor. So VT naught is usually between minus 5 volts and 5 volts. It depends on the type of transistor you use. If it's an on-chip transistor, it's usually around 0.7 volts. And if it's what's called an enhancement mode NMOS transistor, it's going to be plus 0.7 volts. There's such thing as a depletion mode NMOS transistor where we can actually control this VT naught to make it negative. And so in that case, usually it's minus 0.7 volts, but no one really uses those transistors anymore because what they use are PMOS transistors as a complementary device. So I'm about to talk about a PMOS transistor, but I thought I'd tell you this anyway here. For your lab, because you're using off-chip MOS transistors, well, they're in little chips, but you have to access them using terminals off-chip. Those types of transistors are usually power transistors, and so they have larger threshold voltages, so somewhere between minus 5 volts and 5 volts for those. I should also say gamma is typically between 0 and 3, and the units of that is square root of volts. That comes about because you see these square root signs right here. And then finally, 2 phi f is between 0.3 volts and 1 volt, but for us it's generally 0.6 volts. Okay, so that's the threshold voltage equation, and with that, we're finished talking about the NMOS transistor, but we're not finished talking about MOS transistors because very important for our circuits that we'll see later on is the complementary transistor to the NMOS transistor. And so that is the PMOS transistor. Okay, so what is a PMOS transistor? It's basically the reverse of an NMOS transistor. So if you know NMOS transistors, just reverse everything. And so what does that mean? Look at this picture here. This picture is the same as my NMOS transistor, which I'll back up here just to show that NMOS transistor. The only difference is now instead of N plus source and drain, I've got P plus source and drain. Instead of a P-type silicon substrate, I have an N-type silicon substrate. Okay? And because I'm using opposite in basically all my doping concentrations, the device works sort of in the opposite fashion. Right? So the physics is basically the same, but the carriers, instead of electrons, they're now holes. And the voltage polarities reverse. And so for this PMOS transistor, if I wanted to get this functioning the way you usually see it in a circuit, then now I would put ground on my drain, and I would put a high voltage on my source. And so in this case, maybe this will go to VDD, which could be my supply voltage here. But at any rate, this will be the positive voltage here, more positive than what I have on my drain. Okay, the gate voltage that I'll put is going to be less than this VDD. So if I'm applying VDD here, then for my gate voltage, I'm going to want to apply something less than VDD, so I can sort of draw it like this. I would put some VSG on VG. That's going to be less than the voltage that I have, well, the VG voltage would be less than the voltage that I have on VS in order to get this to work correctly. And VDD, again, when I shows VDD, and I think you've seen some of this before too, but VDD is usually what we call our supply voltage for MOS circuits. For bipolar circuits, that'll be VCC. And so what happens when I do this, I'm basically putting a more negative voltage on my gate than was on my source, and so that's going to create negative charge in my gate. I don't know if you could see it, but I'm drawing little negative signs in my gate there. Okay, and so that negative charge, of course, that's going to be electrons. in my gate. And they're, of course, mobile. And so what's going to happen here for my bulk here, VB, I'm going to want to put the highest voltage there. So opposite to my NMOS case where I wanted to put the lowest voltage there, I want to put the highest voltage here. Why? Because my effective diode is going in this direction. And I don't want to turn that diode on. There's a diode here too. Right, I definitely don't want to turn that diode on. I need that to be reverse biased. So I'm going to make the N part higher voltage than the P part here. And of course, since it's reverse biased, you know what's going to happen. You know that we're going to generate a depletion region. Around my diodes, basically pushing, whoops, this will be a depletion region that's going to be positive charge. So we're basically pushing out electrons when we form this depletion region of positive charge. And the same situation here. In the channel, we're pushing out electrons, and what's left are atoms that have lost their electrons, and so they remain with positive charge. At least initially, that's what forms the positive charge in the substrate. But as I continue to raise my gate voltage, I should have used a different color for that, but I guess I'll do that now. Uh-oh. So if I raise my negative charge in the gate, you see I'm making some of the negative charges red here. What that's going to do is eventually it becomes more difficult to create positive charge out here, far from the gate. And so what happens is you create that positive charge very close, and these will be holes. And some of those holes you could just steal from the drain, from the source or drain in this case here. And so this part here is a channel of free holes, which you'll get in the linear or saturation region. So everything is very, very similar to what we get in NMOS devices here. So just to label everything here, this is fixed charge in what we've been calling a depletion region, which means we depleted the mobile carriers, and that's occurring there and here. And then I've got this mobile charge in the channel. And so obviously this is going to be a transistor that's going to work very similar to the NMOS transistor. All the physics will be the same, except now it's holes, not electrons. And now your threshold voltage, VTP, that we talk about, this is now going to be a negative voltage for, at least for what we'll call an enhancement PMOS device. Okay, so that's the physical picture there. And since this is so similar to the NMOS device, I'm not going to go through the derivation of all of its equations, but rather I'm just going to throw those equations at you just the same way that I did when we started this whole thing for NMOS. For NMOS, I threw the equations at you, then we derived them. For PMOS, I'm throwing you the equations. I'm not going to derive them because the derivations are exactly the same as NMOS, except you just substitute holes for electrons, vice versa. And so for the PMOS transistor model, though, you want to look at a few distinguishing features. So in this case, this is the model. So usually when you draw a PMOS, the source you still have an arrow with, just like we had with the NMOS device model. Except notice where this arrow is going. With the NMOS, the arrow was down here, was going out. This arrow here is going in, but what it's really trying to tell you is the direction of the current. Right? So like I said, the source is at a higher voltage than the drain now. If the source is at VDD, the drain is at ground in this example here. So if the source is at a higher voltage than the drain, then currents want to flow from top to bottom. And when we draw our circuits, this is important here, but you know, if you miss it now, you'll get it again later on when we actually do our circuits. Every time we draw our circuits, we always put the highest voltage at the top and the lowest voltage at the bottom. because this is more like a waterfall or something, right? Water will flow from high points to low points due to gravity. In this case, electrons or holes, the current will flow from a high voltage to a low voltage. And so that's why we want to put the high voltage up top. And so that we'll always draw things that way when we are drawing circuits. And so, for example, for an MOS circuit, I may draw an MOS circuit that looks like this. For a PMOS circuit. This is actually going to be one PMOS circuit that we'll work with later on. And so I'll have some kind of resistor there. I'll have maybe an input voltage and output voltage here, but notice that that arrow is telling me which way the current is going to flow. Because I got the higher voltage on top, the current will flow this way. And in this case, for PMOS, I have to call this ISD because this is the source and that's the drain. Okay? And you can sort of see the voltages being applied. Instead of VGS in this case, we're interested in VSG. And I'm missing a negative sign here. Okay, and we're interested in VSD across this. And like I just said, we're interested in ISD, flowing downwards. And so the equations are pretty much the same as the NMOS equations. In the cutoff region where my VSG is less than the threshold voltage, IDSD is 0. Okay, when in the linear triode region, we're now giving us a VSD that's greater than our threshold voltage. Sorry, a VSG that's greater than our threshold voltage, a VSD that's smaller than VSG plus VTP, and that gives you an equation very similar to the NMOS equation in this case. And so all my equations here are assuming that VTP are negative here. Right, so this would be this, whatever voltage this is, effectively minus a voltage here. And so they do work out to be pretty much exactly the same equations as the NMOS equation. This is the kind of thing you kind of have to stare at for a while and compare the equations to get used to this. I guess the best way to really learn to use these equations is to solve problems. And so that's why we're going to give you some homework problems, and a lot of them, that try to get you used to using these equations for both PMOS and NMOS. This is the saturation region equation for PMOS. You can see a lot of similarities with the NMOS saturation region equation. And with these equations, just like with NMOS, I define all of the variables right here. So you have all the information you need to be able to work with PMOS. Okay, it came very fast, but the derivations are all the same for NMOS. We don't have time to rederive them. So I guess enjoy your homework problems while you study PMOS devices with NMOS devices. But right now what I want to do is move on to the next topic here, the other transistor that you're going to be using, the one in fact that you use more of in lab because they just work better in discrete circuits, and that is the bipolar transistor. And so I should say they're both very useful transistors. The NMOS transistor, MOS transistor, they are used more for fully integrated circuits. And so that big CPU chip you've got in your computer or your phone, that's basically all NMOS, or basically all CMOS. Both NMOS and PMOS make CMOS, complementary metal oxide semiconductor technology. We'll talk about that too. For a lot of discrete circuits though, a lot of it is bipolar. And a lot of this has to do with bipolar circuits are more resilient to electrostatic discharge. That's when, say, you walk around, especially in wintertime, dragging your feet on the rug, you develop a charge, and then you touch a transistor. You touch that NMOS transistor, it's dead, because there'll be too much current flowing through it. You touch the bipolar transistor, chances are it'll survive. So for off-chip applications, bipolar transistors just work better. That's why in this class, when you start doing transistor circuits, you'll be using bipolar transistors in the lab. There's a reason behind the madness in our lab. We have to use bipolar transistors to allow you to design some pretty cool circuits. Otherwise, if we just did MOS, the circuits in the lab would not be cool enough, in my opinion. So both transistors are important to understand. If you're the type of person that likes to take apart your TV or take apart, different things, and you want to replace transistors, you'll probably be replacing bipolar transistors. Although in some cases you'll be replacing some MOS, especially in power applications where you have power power MOS transistors. In the end, it's good to know both, and you're going to know both by the end of this class. And so here's your bipolar junction transistor. And so historically, I should also say the bipolar junction transistor, I would say conceptually the MOS transistor came first. It was the most natural way to think about making a transistor. Basically a device that is on-off controllable. You can control the current, a voltage-controlled current source. But historically, they had trouble getting MOS circuits to work, MOS devices to work. There were all sorts of issues with technology. There were too many, I would say, non-idealities in creating oxides over silicon. Too many interface states, I should say, and contaminants that didn't allow us to make NMOS and PMOS transistors very easily at first. But we did learn how to make bipolar transistors, an alternative way to create a transistor. So that's why bipolar transistors came first. Over time, MOS transistors have taken over for fully integrated applications like CPUs, mainly because they consume less power. And that was the big thing. It was the low power consumption of NMOS transistors that allowed them to be dominant in these large integrated circuits that have billions of transistors now, right? If you use billions of transistors, each of them better consume very little power. Otherwise, it's going to take hundreds of watts to power your whole circuit. And sometimes it does in some computers. But, you know, eventually it'll get to 1,000 watts and then the whole thing will just burn itself up. Okay, so that's the reason why MOS is preferred today for these large integrated circuits, but bipolar is preferred for your off-chip stuff, of which there's still a lot of applications that use this. And so here's your bipolar transistor. It's basically a couple of PN junctions. And so if you look at this circuit that I'm showing right now, right, I effectively have an N piece of silicon connected to a P piece of silicon connected to an N piece of silicon. It says N plus there, and it really is N plus. We're changing the doping concentrations between these for reasons you'll see a little later on. But effectively, I've created back-to-back diodes here. And so I can draw that to emphasize that. I got a diode here. I got another diode here. And they're back-to-back. And so it looks like you're never going to get any current out of this. But in actuality, you can get current depending on what voltages you put between this P and that N and this P and that N. So for example, if I take this junction here, which I can call the collector base junction. So this N type up here we call the collector. The P type we call the base. This N plus down here we call the emitter. And the symbol for this transistor looks like this. It's a lot like the MOS transistor, but I don't show a gate because it really doesn't have a gate. It just has a terminal going straight to the P-type base. It's got a terminal going straight to the N-type collector and a terminal going to the N-plus type emitter here. But you notice I can apply several different types of voltages across this. I could apply a voltage across what's called my collector base junction, abbreviated CBJ, which I will write out here, that this is my collector base junction. And then, of course, I've got the other junction, which is my emitter base junction. And there's a reason for all of these names. You'll see them as we start talking about this device here. But this is the basic device that I have. And this is an NPN transistor. NPN is sort of like NMOS when we start designing circuits. Okay, so that's a transistor structure. I could do the same thing down here. So if I scooch down here, and if I put a P plus, N, and P, now I have what's called a PNP device. And so up here, this is an NPN transistor. Down here, just because of the materials that I'm putting together, that's a PNP transistor. And these junctions, again, I can define, and I can define diodes here, but now the diodes for this are going the opposite direction to the diodes up above, right? Now the diodes are sort of facing each other inwards here. And now I've drawn the emitter base junction above. And so you can see the symbol for this transistor. Again, like the MOS transistor, the arrow is telling me which direction the current is going to flow in this. And I understand you don't know how currents flow yet. We will talk about that in a bit. But I'm just showing you the actual physical device and the symbol. Okay, and so this, again, I can call this my emitter base junction. And down here, that's going to be my collector base junction. And that summarizes then my PNP transistor. Okay, like I did for NMOS, I'm going to focus on the NPN transistor. And then the PNP transistor, a lot of its stuff is going to come sort of, by analogy. It'll sort of be the dual, the opposite dual, I suppose, as the NPN. But let's now take a look at a couple things before looking at the physics. And so what I'm really just throwing at you, sort of the nomenclature that people use for these devices. So back up to the NPN transistor up here. And so I can apply different types of voltages across the base to collector and the base to emitter. And if I think of each of these junctions as diodes, I can think of either forward biasing or reverse biasing each of these diodes. I've got two diodes. That means I've got four different combinations of forward and reverse biasing across each of these junctions here. And so if I reverse bias, indicated by R, so here's my legend up here. F means forward bias, R means reverse bias. But if I reverse bias both junctions, that's the cutoff mode of this transistor. I can call that region of operation 2. So that's when both diodes are off, and I think you can predict right now how much current will flow. No current will flow in this case. This is when we've turned the whole thing off. If I put a forward bias on my emitter base junction down here and a reverse bias on my collector base junction, this is going to be the mode of operation where we're almost always going to use this device. And this is called forward active, widely used in analog amplifiers. You will get to know this region of operation in this class very, very well. Okay, I could do the opposite thing. I can reverse bias my emitter base junction, and I can forward bias the collector base junction. And so again, which is which depends on the doping concentration. The emitter is the one with the highest doping there. But if I do this, the transistor will still work. You can make it work upside down. It just won't work as well as the forward bias direction. And so what we're telling you right now is that this transistor is not quite symmetric, but it'll work in both directions. But you don't want to use it in the bad direction because its properties just aren't going to be very strong. You're not going to be able to get as much amplification. You're not going to have as wide a bandwidth in the eventual amplifier that you're trying to make. And then finally, there's a saturation region. This is where you've turned on both diodes. So you forward bias both diodes here and here. That's also not a good place to work in. And so we're not going to want to work in saturation. We want to work in forward active. So this is where we'll spend most of our time. That was supposed to be usually. We will usually be here in that region. So you can also graphically think of all of these things here. And so as you get used to this, you can think of these on an XY plot, where this is the VBE voltage versus the VCB voltage here. Where if I put a positive voltage on VBE, which means I'm forward biasing the emitter base junction, and a positive voltage on the collector base junction, that's forward biasing that's saturation, just like this, and so on and so forth. Forward active is down here, where I want a positive voltage across VBE and a negative voltage across VCB to reverse bias the collector base junction. Okay, so a lot of this, is still, I know, probably cloudy to you, and so let's clear things up just a bit. Let's now focus in on the cross-section of this device, similar to what we did with MOS. And we're going to do this a bit faster than MOS. And rather than write out a lot of the stuff, I'm going to use some prepared slides here, mainly because we've already talked about diodes. We've talked about how current flows in diodes. And so now what we're most interested in here is the currents that flow in the PN junctions when we bias these differently. The currents are still going to be dictated by the same equations that we had for diodes. But now what we're more interested in, which currents will flow. And so as an example, we can take a look at the cutoff region. So this is that region where for each diode, what we're doing is we're reverse biasing them. So in this case, it's an NPN transistor, so N plus in the emitter, P plus in the base, N in the collector. And so let me sort of label these here. So that's the emitter, that's the base, that's the collector. And so I've reverse biased both of these, which means I'm not getting any current flowing across this junction. I'm not getting any current flowing across this junction. So in the end, both diodes are reverse biased, no current flows, period. And so this is a very simple region of operation. And if I wanted to take this transistor symbol, right, where the collector is here, the base is there, the emitter is there, okay, the emitter is the part with the N plus region, then this is the equivalent circuit. Pretty simple. It's just a big open circuit. And so if you ever have a circuit that uses this transistor, maybe you've got resistors and supplies around this, I would put those resistors and supplies around here, and then I would have an open circuit there. So this is the ideal model. This one is the real model, I suppose. It's real because it takes into account the fact that there are still very small reverse currents. So it includes the tiny reverse currents. Remember that we get when we reverse bias a diode. If you recall that diode transfer function, it looked like this. So if this were the voltage across the diode, and this were the current in the diode, it looks something like this. Boom. So the current goes up very fast, but here you have a little bit of reverse current here. How big is that reverse current? Well, it's on the order of, say, 10 to the minus 18 amps. That's tiny, right? To me, that's nothing. So you'll see what happens when we look at circuits. We're going to neglect that. And so instead of this, we're basically going to be using that ideal model every time we see a circuit in this class. Okay, but this is the reverse bias region of operation for a bipolar transistor. Okay, that was pretty simple. Let's now move on to a more interesting region of operation, so the one that I said we would use most, and that is the forward active region. Okay, so here's an example of forward active. And so I have, again, my base emitter collector. I've got a junction across this here. And now what I'm doing is I'm forward biasing this diode because I'm putting a positive voltage on the base, a negative voltage on the emitter, so plus on the P, minus on the N. And if I do something like that, you know current is going to flow. Okay, so I put a negative voltage there and a positive voltage on my base. And so I still have my positive voltage on my base, but now what I'm doing here is, in order to forward bias this, what I want to do is put a negative, make this VBC negative. So VBE in this case, I make positive in order to forward bias this. So I made that positive. This VBC, I'm making negative here. And so when I make that negative, effectively, I'm creating wait, VBE is positive. So the collector base current I want to make negative. The negative point is right here. Making VBC negative means making VCB positive, which means effectively what I'm doing is I'm putting more positive charge here than I have on the base. So in that way, I am reverse biasing this diode. Okay, so this diode is reverse biased. Let me think of how I'm going to create my colors here. Let me use a very light color to draw my diodes here. And so you know that one of my diodes is going this way. And you know that my other diode is doing this. Okay, this diode is forward biased. I think I'll even just point up here. This diode is forward biased. This diode is reverse biased. Okay? And so what happens? When I reverse bias that diode, you know what's going to happen on that side. I'm creating a lot of depletion charge. I have depletion charge here as well, but here I'm going to get a lot of depletion charge. And so let me just draw that depletion charge. This is, I've got p-type on the inside, so that means that I'm going to push holes away, which means I'm going to be left with negative static charge right here. And this is n-type, of course, out here, and so I'm going to push away electrons, and I'm going to be left with static atoms that have positive charge. Okay, so I create that depletion region here. I do have a depletion region here, but I'm not going to draw the charge because that would clutter things, because I want to draw some other things there. But let me just label this here, that I do have depletion regions here, things that we've seen before. Okay, now let's talk about the currents that are flowing in this. And so if I have this forward biased, what's going to happen? You know that I'm going to have electrons from the emitter side. The emitter side, which is N plus, it's got a lot of electrons there. They're the majority carriers. Okay, they're going to inject into the p-type side, in which case they'll become much less populous than the holes in the base, the p-type size there. And so they might recombine with the base. But what's really going to happen is they're going to head on through the base. They're going to see all of this here, the negative and positive charge, negative and positive static charge. What does that create? That creates an electric field that's in that direction. Okay? So if I see a lot of electrons suddenly coming across this depletion region, so being injected in this way, those electrons are going to do what? They're going to come in. They're going to see some holes in the base, and when they see some holes in the base, they will be annihilated by those holes. So I can draw this in here, there, and I can draw a small component of this current. Electron current comes in here and gets annihilated by holes. So this is electron current I'm trying to draw here. Electrons. But from the bottom side here, from this electrode contact from the base, what's going to happen is it's going to these electrons will combine with holes coming the other direction. And so those are electrons, those are holes, and they will annihilate each other. So they'll recombine and annihilate. So let me use a different color there. So what happens here is I get what we call recombination. Of electrons and holes. Okay, that's one component of current of electrons coming through this. Now, this other component of electrons, notice I haven't shown these recombining because these will statistically be able to get through the base if the base is thin enough, and usually you make the base thin enough to get to this point here. When they get to this point, they suddenly see an electric field in this direction. They love that. When they see an electric field in this direction, that's just going to sweep them all the way into the collector side. So these electrons that successfully get through without seeing a hole, oops, let me make that the right color. First, let me get rid of that and go back to red. These go all the way here and they make it to the collector. Okay, so these are all electrons that came all the way from the emitter, crossed the base, and made it to the collector. This is the current that we care about right here. And you'll see in a second why, well, not in a second, but a few lectures down the line, and also the next lecture you'll see why we care most about this current component. Now, to finish up all the current components, there's one more component of current that we have to talk about, and that is the component of current where holes, of course, inject into the emitter. And so I've got one more component of holes that inject into the emitter. And so this is also coming basically from the base connection here. But these are holes that are going in that direction. That's injected current going into the emitter. That's going to be smaller than this current up here because we've doped the emitter N+. Okay? And so I'll go back and take a look at those equations. We're over time right now, so I won't look at the equations right now. But I wanted to at least show you all the types of currents that are flowing. I've got electron current that's injected into the base that gets to the collector by being swept by this electric field. I've got electron current that doesn't get through the base. It recombines with holes. That hole current's coming from the base. And then I've got some more hole current coming from the base that's being injected into the emitter. In the end, what I want to have the best performance for this transistor to make the best amplifier, I want this electron current to be much larger than all of these currents that are going into the base. I want the collector current to be a lot larger than the base current. That is the art of making a perfect NPN transistor, and that's an art we'll talk about more in the next lecture because we are out of time right now. So I will see you in the next lecture.